turbo engine running. Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the programme where we bring you the latest breakthroughs in science, technology and medicine with me, Chris Smith. And today we're exploring the science behind the atomic bomb and how it altered the course of modern warfare. Now, the name Robert Oppenheimer may not have been that familiar to many people before the release of the Hollywood blockbuster recently bearing his name, but he was the physicist who worked to realise the industry of British, American and other scientists in creating the atomic bomb. It's now the anniversary of the date 78 years ago when the United States dropped 2 nuclear bombs on the Japanese cities of Hiroshima and Nagasaki to end the Second World War. In the present, the Russians have continued to rattle their nuclear sabre following the invasion of Ukraine. So how do these weapons work? What's their history? And what will be the fallout, both literally as well as metaphorically, if Vladimir Putin were to press the big red button? Well, that's what we're going to explore this week. And to kick us off, here's Will Tingle.
I am become death, the destroyer of worlds. It's a quote etched in history. Originally from the Hindu scripture, the Bhagavad Gita, Robert Oppenheimer, dubbed the father of the atomic bomb, gave this quote when he recalled witnessing the first successful nuclear detonation on the 16th of July, 1945. About 3 weeks later, on the 6th and 9th of August, the US dropped nuclear bombs on Hiroshima and Nagasaki, respectively. The death toll of the combined attacks varies by source, but they could have killed as many as 220,000 people, most of them civilians. The bombs dropped on Hiroshima and Nagasaki, and the deaths they caused, stand as decades-old reminders as to the horrifying powers of nuclear weapons and the utmost importance of them never being used again. But, for a moment, let us imagine the unimaginable. What would happen if a nuclear bomb was detonated in a populated city? I asked Alex Wellerstein, historian of science at the Stevens Institute of Technology and creator of NukeMap. And when studying the effects of a nuclear blast, everything has to be taken into account. We refer to nukes as the bomb, but nowadays there are far more than just one.
You sort of have on the menu, very low end would be like a terrorist nuclear weapon, maybe a kiloton, maybe 10 kilotons. 10 kilotons is somewhat like the World War II nuclear weapon. So even though we're talking about low, that's still pretty powerful. If you're talking about, say, the Russians or the Chinese, you could range probably in the hundreds of kilotons, potentially to the low megatons, so millions of tons of TNT. And if you're talking about a terrorist, you're talking about a weapon that's going to be set off on the ground, and that changes things. If you're talking about a state and your target is like a city, then the weapon is probably going off in the air because that maximizes the kind of damage that would be done to a city. So there's a lot of possibilities here, both in terms of the weapon itself, but also how it's delivered and how it's even targeted. And those change pretty dramatically what kinds of consequences you're worrying about.
So with all that taken into consideration, what happens in the moments after detonation?
When the weapon goes off, it's going to be essentially almost instantly transformed into a fireball. It's not instant, it takes about a millisecond, but from human perspective, it's pretty instant. And that fireball is going to be putting out an intense amount of heat and an intense amount of radiation. Inside that fireball, that's now going to be turning into that mushroom cloud. That's what the mushroom cloud is. It's a sort of cooling, rising fireball. And there's going to be a lot of really nasty radioactive things inside there. If it's detonated on the ground, it's going to have sucked up a bunch of dirt and debris and who knows what inside of it. The radioactive bits are going to attach to that and sort of fall out of that over the next few hours. And that's going to be the delayed radiation, the nuclear fallout, which will be contaminating and go wherever the wind blows. That radiation is going to be relatively quick blast. The heat is going to be searing for several seconds, depending on how powerful it is. Searing enough that if you're within vast distances of it, you could get a burn just by being in the line of sight to it. There's going to be an interaction between the radiation and heat of the fireball and the atmosphere that is going to create a blast wave. You're basically dumping a lot of energy into the air, and that's going to create this sort of expanding wave of sort of superheated, super compressed air. And this is like a wall of pushing pressure. And as that expands out, it's going to be sort of shedding its energy. It's going to be getting weaker the further it goes. But depending on how far you are, that's a lot of pressure being put out sort of in a big wave or wall. And that's going to be doing a lot of breaking windows. If you're close, it's going to be knocking buildings over. So those are your sort of four major effects.
A truly horrifying concept on all levels then, but the danger isn't over once the mushroom cloud clears. Alex mentioned the immediate blast of radiation from the bomb, but that radiation hangs around afterwards and can travel very far from the source.
So the radiation can go very far from ground zero depending on the size of the bomb used. It can go hundreds and hundreds of miles and be still pretty dangerous. The radiation that's coming down in fallout is going to look something like a ash or snow. It could be a rain, depending on the atmospheric conditions. And depending on where you are, some of that in the first few hours in particular is going to be so radioactive that it's, deadly from a very short exposure. The really tricky part about this is that the decay of that radiation is relatively fast compared to what people think it is. It's not going to stay hot, hot, hot for hundreds of years or anything like that. Within 48 hours, it's less than 1% of what it was at 1 hour, for example. But it creates this sort of chronic risk in that some of that stuff is radioactive enough that you wouldn't want to live with that radiation. You might be able to travel through that zone and not have any harm come to you. But if you lived there, especially large numbers of people, especially vulnerable populations like pregnant women and children, then you're going to start seeing the cancer rate go up, up, up over time. So you have a large area that is going to have a very short-term danger from the immediate hours after the bomb, but then also have this long-term contamination problem.
Sobering stuff. Now, Alex paints a rather grim picture, so let's take a step back. We've been developing different ways and levels of harnessing atomic energy in weapons for the last 80 years or so, but our discovery of the atom and its potential to release massive amounts of energy goes back a lot further than that. Frank Close is a physicist at the University of Oxford, and I asked him how we went from the discovery of atoms to the creation of the most powerful weapons ever made.
By the end of the 19th century, chemistry was a pretty well-defined science, and the idea was that all matter is made of ultimately atoms, and the belief was that the atoms of element were all identical, that they were permanent, unchanging, and there was nothing smaller than them. But it was in the 1890s when the discovery of what we now call radioactivity occurred completely out of the blue, that the whole of what I would call the nuclear age ultimately began. Henri Becquerel in Paris discovered that salts of uranium spontaneously emitted some radiation which would fog photographic plates that were hidden in the dark without any prior stimulation. And it was the Curies in France who really got to work on this and discovered that there were other elements also which had this phenomenon of pouring out energy continuously. And it was the Curies who gave the name radioactivity to it. And it's there that the energy locked inside the atomic nucleus being released in radioactivity was the origins of this weird energy that had been seen in radioactivity. And the question, of course, then emerged, as there is indeed this huge reserve of energy buried inside atomic nuclei, is it possible to extract it and make use of it?
Who had that insight, Frank, that said, well, there's all this energy locked up in there. We know it shows its hand sometimes with some of these naturally occurring radioactive elements. But who was it who began to say, can we get at it?
The first measurement that showed that it was indeed huge in magnitude was indeed due to Ernest Rutherford around 1900. When he did the sums, he found that the amounts of energy that had been liberated, say, by some amount of matter, was millions of times more than chemistry could understand. And so it was Rutherford's measurement of the energy emitted in radioactivity that gave the first clue to there being vast amounts of energy inside atoms. It was only after he had discovered further the existence of the atomic nucleus, it then became clear that it was the nucleus where this energy resided.
That is the turn of the century. We know that the bomb goes off in the 1940s. So what fills that gap? People like Rutherford speculate we might be able to harness this energy, but how did they go about it?
So by the 1920s, Rutherford and the beginnings of nuclear science had identified that the nuclei of all atoms are made of protons and neutrons. The radioactivity, we now know, was rays of particles called alpha particles, and by beaming these alpha particles at the nuclei of atoms, they discovered that these nuclei changed. They could break up and in the process liberate some energy. The problem was that it was so slow, there was no obvious way that you could ever make use of it until 1932-ish, I think, when at Cambridge, they built the first of what began to be known as atom smashers. And in the course of doing that, they discovered that significant amounts of energy were released when you smash these things apart.
So who did what next? Because I've been to Argonne National Lab and I'm pretty sure that there's a copy of a letter there, and I think Einstein penned it to the president of the US, setting out what could be done with this sort of physics. And what was the thinking that led to him penning that letter? And then what had been happening in the background for people to begin to say, right, well, let's try and harness this and make this into a weapon?
The discovery of nuclear fission took place at the end of 1938. The thing is that to produce, let's call it explosive amounts of energy, ordinary uranium is no good. There are two varieties of uranium for our purposes, one called uranium-238 and one called uranium-235. And it's the 235 that's is potentially the explosive sort. The problem is only 7 atoms in every 1,000 tend to be uranium-235. So to make an explosion, you have got to somehow increase the percentage of uranium-235. In the jargon, that's known as enrichment. Surprisingly, it seems, nobody asked the question, but if somehow you could make a lump of pure 235, how much would you need to make an explosion? And the first people that did that was Rudolf Piles and Otto Frisch at the University of Birmingham in 1940. And to their astonishment, they discovered that a lump about the size of a grapefruit would be enough to have an explosive power equivalent, in their words, to 1,000 tons of dynamite. And they also realized that it would produce radiation, which would be potentially lethal. And this was a weapon that would completely change the nature of warfare. That was when everything moved across to North America into what became known as the Manhattan Project. And the British team went across there as part of that, which eventually led to the development of the atomic bombs at Los Alamos.
And how does Oppenheimer get involved?
Oppenheimer is popularly described as the father of the atomic bomb, which in my opinion is the wrong metaphor. I would say he's more like the midwife. It was Oppenheimer, by directing this huge program of scientists and engineers in those last years, 43 to 45, that led eventually to atomic bombs being produced. And so Oppenheimer was in charge of the direction of these teams of scientists and specialists that led to the construction and eventually detonation of these weapons.
So that was splitting atoms. We've dwelled very heavily on splitting atoms and fission so far. So what was the insight that led to someone saying, well, let's fuse them together and make an even more powerful bomb?
The idea that you might be able to do this was first articulated in a discussion between Edward Teller and Enrico Fermi in the States around 1942, I think it was. The conventional, what we call atomic bomb, where you fission uranium, these neutrons that are being produced, which are essential to making the chain reaction happen, they escape the lump before they can really do their stuff. You need a large lump so that the neutrons keep producing energy before the lump is destroyed. A fusion weapon, a hydrogen bomb, if you like, in principle, there is no upper limit to it. I mean, the sun, for example, shows if you had enough hydrogen, you could have something burning away like the sun. A big technical question is, the sun has been burning for 5 billion years. Can you speed the whole process up so that it liberates its energy in a fraction of a second? It was Enrico Fermi who was present at the Trinity test of the first atomic bomb, he had the insight in the process of the explosion, the atomic bomb produces a temperature of tens of millions of degrees. And the key thing to making fusion happen is that you need such temperatures. And Fermi's insight was in the moment of the conventional atomic explosion, that creates the heat. And so he saw the possibility that an atomic explosion could provide the spark to ignite the fusion bomb. The technical features of making the hydrogen bomb, however, are incredibly complex, and there's still a huge amount of secrecy over them. It wasn't until the early 1950s that some of the key steps really were found, enabling the thing to be done, and much of that is still secret today.
Frank Close. And Frank documents more of the story that we've just been hearing in his book, Trinity, The Treachery and Pursuit of the Most Dangerous Spy in History, which is available now. Now, Frank just spoke about the jump to the next generation of nuclear weapons, fusion bombs. These were first tested down in the South Pacific in the 1950s, and Ken McGinley, who was still a teenager at the time, told me what it was like to witness one from his military base on Christmas Island.
I was standing on the beach. There must have been about maybe 300 or 400 servicemen standing there waiting for the bomb drop. We didn't know what to expect, obviously. The plane did, I believe it was about 2 dummy runs, and it was very, very hot standing there with the boiler suit. Was standing for over an hour. Finally, the all clear was given, and the countdown began. 3, 2, 1. Then all of a sudden, there was this magic flash. We were told to put our fists into our eye sockets, not to look at the bomb. And when it went off, we were given the order to turn around and face the bomb. And the heat from it was tremendous. But the thing that I noticed more than anything else was I could see the complete bone structure of both my hands, even through closed eyes and clenched fists. That was quite scary, and I think natural reaction, myself, like other people did, we took our hands away. I felt it actually burning my body. The thing that followed after that, of course, was the shockwave. By that time, we were all sort of talking to each other, and when the shockwave hit us, some of the men fell down and knocked over on their back, and we all just, some of them were actually crying. And when we saw the bomb, which was unbelievable, all different colours, into a giant mushroom, and then the next thing, of course, it was coming right towards us.
How far away from the detonation point were you standing?
I think roughly about 15, maybe 12 to 15 miles.
Were you at all concerned about danger from this? Obviously there was the shockwave and that kind of thing, and the heat, but the invisible danger of the radiation, people were aware of that, were they?
I had never heard the word radiation in the year that I served on Christmas Island. I had never heard about dangers. We didn't even know anything about what we were going to see until we were 3 weeks out at sea. And I remember Sergeant Ward gathered us all up on the deck that day, and he told us we were going to witness bomb tests. We had never heard of Hiroshima or Nagasaki, anything like that. At our age, the first page you turned to in a newspaper was a back page to look at the sport. I do remember when the bomb went off and we were going back to our tents, that I saw 2 men who were dressed. They had the Wellingtons on, the full gear, the white boiler suits, thick black glasses, and they were telling us, because it started to rain, they told us to get under cover. It was so warm that day, we just took our boiler suits off and threw them into a big pile and started walking back to the tent to get a refreshment. We always kept our beer in the tent there. They were telling us to get under cover, but we didn't know why. But we believe it was actually maybe radioactive rain that was falling down on top of us. It was quite heavy, big droplets, by the way, and it was nice and cool, actually, to get nice cold water on us after standing there for almost 2 hours. I woke up about 2 days after the first bomb test. I couldn't open my eyes up. My face had quite a few blisters on it, and so had my chest. I went along to the MO, and there was quite a queue of guys standing there. We were all given this sort of clear lotion to rub on our faces to maybe take away the blisters. But it was okay, actually, and after a couple of days, it all cleared up again.
Extraordinary story, isn't it? Ken McGinley there. Ken turns 85 next month, so happy birthday next month, Ken. And if you'd like to hear the full account of Ken's experience and his life in the aftermath, actually, you can look up our special editions or in short podcasts on the Naked Scientist website. You can grab my full conversation with Ken there. Also subscribe to the special editions podcast we've got wherever you get your podcasts, and it'll be on there imminently as well.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith, and this week we're taking a closer look at the history and the science of nuclear weapons. And we've looked so far at the destructive development and force of nuclear bombs, but the detonation of such a device is not just a physical act, it's also a political decision, and one with terrifying consequences. And in the current climate, as Russia continues to wage war in Ukraine, the nuclear threat is very much back in the public consciousness. I've been speaking to General Sir Richard Sheriff, who served as NATO's Deputy Supreme Allied Commander in Europe between 2011 and 2014.
The Russians integrate nuclear thinking into every aspect of their military doctrine, and indeed their nuclear command and control is delegated down to army district or district level. We've watched them practice this. I mean, for the last decade or so, every 4 years or so, the Russians have run the so-called Zapad exercise. And very often the scenarios have been the Russians biting off a chunk of or all of one of the Baltic states, which of course are members of NATO. So that means that NATO would be treaty duty bound to come to the aid of them. They take them over, and then anticipating a NATO response, the Russians would practice the deployment and potential use, I say potential only, of a tactical nuclear warhead. The basic message being that if you come back at us to recapture or have a go at us in the Baltic states, we'll drop one of these things on a NATO capital, Copenhagen or Warsaw or Berlin. And the idea being that you threaten your opponent, and so NATO backs off. Because such an outcome would put NATO in an extraordinarily difficult position, because the only response would be a nuclear response.
So it's kind of the first mover advantage situation here.
It is indeed the first mover advantage.
Most people, when you say nuclear weapon, they tend to think of the huge mushroom cloud going up and that kind of thing. But these weapons come in a range of different sizes and shapes and forms, don't they? So we're not necessarily talking about capital city destroying weapons. They could use things which are much smaller and devastating more locally. And is that what he's posturing with at the moment?
I don't think we should downplay the threat here. I mean, the use of a tactical nuclear weapon in its immediate vicinity would be absolutely devastating. It's indiscriminate as well because of the nature of the fallout and the radiation that follows. But I think we have to, if one can put it into perspective, Ukraine is a big country. That front line is 1,000 kilometers. It's a vast amount of Ukrainian steppe. Would it change the dynamic militarily? Locally, absolutely it would. But it would not stop the Ukrainians doing what they need to do.
It would also be on his own doorstep, wouldn't it? Because if the intention is to take over Ukraine, arguably piece by piece or the whole thing, you'd end up with a huge nuclear mess in the middle of part of what you've now acquired, and then it would cease to be the opposition's problem. It would be your own problem to clear it up.
Absolutely. And of course, the chances are that if it did happen, it would be released in one of the 4 oblasts that Putin has technically annexed to become part of Russia. So utterly self-defeating. What sort of message does that send if you use a nuclear weapon on territory which you have annexed and whose population is now, you would like to think of as part of your own? I think the other aspect, of course, is it's massively self-defeating from a geopolitical and wider international perspective. I mean, President Xi has made it very clear that nuclear is not on the agenda. It would be a real issue for the Chinese, as probably it would be for the Indians and others. So it would have a major impact.
Therefore, if he did do this, and it would probably be because it was pushed into a corner act of desperation, what would be the retaliative response? What would people do? Would there be a point in retaliating, or would we really gain nothing by retaliating at that point?
I think there has to be a very clear message that any form of nuclear release would invite the most massive conventional retaliation from NATO, and it would bring NATO de facto into the war. And that is not what Putin wants. Now, I don't want to speculate on the nature of that, but suffice it to say that NATO combined could completely annihilate Russian forces. There is communication between Washington and Moscow. I mean, I look back to the time that President Biden went into Kiev, and after he came out, it was released that the Americans had told the Russians that Biden was going in. So there is communication, and that's good. And communication is essential. It's an essential component of deterrence, because without communication, there's always the danger of miscalculation. So communicating the intent to retaliate ruthlessly at this stage of the game is essential.
General Sir Richard Sheriff there. So how prepared are we for a nuclear attack, and what might a response from Western leaders look like? Well, William Albuck is the Director of Strategy, Technology and Arms Control at the International Institute for Strategic Studies, and he's with us now from Berlin. So many moving parts and variables in this sort of consideration, William. What factors are borne in mind when coordinating or coming up with a plan for a response?
It's like Alex was saying at the top of the session, it really matters how the detonation takes place. If it happens very, very high up in the sky, then it's not going to make a very large ground zero. It's not going to suck thousands of tons of debris up into the atmosphere for fallout. If it is a ground burst, if it's an explosion that occurs very near the ground, then it's going to make a huge ground zero, a very, very radioactive zone, and it's going to put a tremendous amount of fallout up, and that's going to make it much more difficult to respond. I would say that the U.S. is fairly well prepared for this kind of incident. I used to work for the Department of Defense, and we actually exercised the nuclear accident response plan across the country. FEMA, the U.S. Federal Emergency Management Agency, actually has a document called the Planning Guidance for Response to a Nuclear Detonation online. It's a 260-page manual for the government, local governments, and federal government to work together to respond to a nuclear detonation. And it was updated actually in June of this year. And that brings together a whole of government response, including Homeland Security, Department of Defense, EPA, the Environmental Protection Agency, Health and Human Services, to work together in a federal coordinated response with the local first responders. Obviously, an incident where a nuclear weapon went off, that would be a national incident that would be run probably out of the White House as the federal command post, with a forward command post set up, an initial operating facility near the explosion site to do the assessment. The government would really be focused on measuring and monitoring and trying to figure out exactly what this explosion was, again, the altitude and the yield, and trying to track where the fallout may go so that they can plan where to put their responses, where to put field hospitals, where to put command centers. There's obviously going to be a huge amount of people fleeing an urban area if it's struck with a nuclear weapon. You need to manage those flows. And you also have to really worry because some of those folks who may have survived the initial explosion may be very exposed to radiation and may themselves be giving off radiation. So you have to do all kinds of planning in terms of containment zones, treatment zones. You have to coordinate a medical response across the entire country. And the federal government also has to get in front of messaging, because for a lot of these folks, you don't want them to flee. You actually want them to shelter in place, because if they go running 15 minutes to half an hour after the bomb explodes, they may be exposing themselves to the most dangerous period of fallout.
Are plans for what could happen off the back of what's going on in Ukraine in place for Europe, for those flanking countries, and for farther afield nations? Because Chernobyl, the nuclear power station that exploded in 1986, we saw the fallout, the radiation landing in Cumbria, in the northwest of the UK. I mean, long, long way away. So the impact is far-reaching, isn't it?
Oh, you're absolutely right. And I think far too few countries in Europe, and I would put the UK in this category as well, have done, I think, adequate preparation for a smaller scale nuclear attack, for a single nuclear explosion, or for 2 or 3 nuclear explosions, because there is a tremendous amount that you can do to prepare and to mitigate the worst possible consequences. And in Europe, especially, as you just pointed out, it's going to require an international response. So I think NATO would be a very natural place to go to do more of this consequence management preparation, to coordinate the medical response now, to coordinate the radiation response now, and communication and everything else you need to do, logistics. All the hospitals in Europe would have to be involved. There'll be more burn patients than there are burn beds across all of Europe. So it's going to need to be a massive response.
With respect to the immediate aftermath medically then, what do we do about that? Because there will be a range of different injurious circumstances. There'll be people like Ken, who we heard from earlier in the programme, who've been zapped and they will be burned. They will be suffering that sort of injury. There will be people who may have been hit by flying debris and glass. It's a more physical injury. There'll be emotional injury, but then there will obviously also be the radiation impact. So what sorts of plans are in place and how do we manage the medical effects?
Right. So in the United States, for instance, they'd be setting up field hospitals near enough to be able to help, but far enough away that they wouldn't be in danger of any kind of radiation or chaos. They would also be using the hospitals across the United States. And I would imagine the same thing in the UK, the same thing in Ukraine. You would have to use thousands and thousands. I mean, you're talking about 150,000 casualties, potentially from 40 kiloton burst. So that means you would need, basically every hospital bed you can get your hands on. You'd have to ask medical staff to work around the clock for weeks and weeks and weeks. So you would need a really, really international, large-scale, coordinated response in Europe. Or in the United States, you'd need, whole-of-country response just to one atomic blast.
And what about the health of the environment? Where these blasts go off, is it curtains for ever using that patch of land again? Does there need to be a certain time elapsed before it can be remediated? Can it ever be remediated? What's the intervention there?
It can be remediated. It absolutely can. I mean, I've stood at Trinity site, the ground zero for the first atomic blast. Hiroshima and Nagasaki are thriving cities today. Radiation diminishes radically with time. So the cost is enormous. It takes a lot of time, but you can remediate, you can rebuild, and you can repopulate the city. And again, Hiroshima and Nagasaki are living examples of thriving cities today, despite the atomic attacks.
So if a person were to find themselves in a situation where this is going to potentially land in their neighbourhood, what can a person do to mitigate the risk of if they're almost at ground zero?
Right. So if you know it's going to happen, then you have to make sure that you don't look anywhere near it. If you look at it, you could lose your eyesight. The advice is if you're outside, that's the worst scenario, lie face down. Wait till you'll feel the flash, you'll feel the explosion, you'll feel the winds coming off. And once that stops, you have 15 to 30 minutes to get in shelter before you run the risk of being exposed to fallout, those radioactive dust particles that Alex was talking about. Better to be inside a car, but still not good. Better to be inside a wooden house, but still not good. Even better to be in a stone building. In the interior, stay away from windows, because as you pointed out before, the windows are going to shatter and that becomes shrapnel that will kill you. The best would be to be underground in a very large stone building or in the underground metro. And you shelter there and turn off your electronics, because the EMP, the electromagnetic pulse, is going to probably knock out your electronics. But if you're far enough away from ground zero, you can probably turn it right back on afterwards. And most nations will have an emergency network that will then communicate with your cell phones, or if you can find a radio, and they'll tell you shelter in place. But you always have to weigh the risk of being outside because of fallout versus the risk of fires, which are also going to be a huge issue. Listen to the central authorities' radio messages or cell phone messages, and then go from there.
William Albeck there. Thanks very much. And that's where we have to leave it this week, but do be sure to tune in next time when we're taking a closer look at food. We all know we're eating stuff that's bad for us, but do we just need to cut down on the portions, or do we need to change tack completely? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening, and until next time, goodbye.